There is one equilibrium constant that we're going to do that's related to KEQ that involves solutions. Dissolving things in water gives you solution equilibrium when you make a saturated solution. So when the solution is saturated, you're at equilibrium. So as NaCl dissolves to form the Na and Cl ions, eventually those ions are going to come back together to reform the precipitate. When the rate of that change is equal, you're at solution equilibrium and your solution is saturated. Now, when you just reach the saturation point, if you've done it perfectly, you'll have no salt and just ions. If you go just a tiny bit beyond that, that's when you start to reform sodium chloride. That was your over the saturation line. Now, since KEQ equals products over reactants, since it equals the NaCl, the Na plus 1, times Cl minus 1 over NaCl, if the NaCl makes up 100% of our mixture, and the NaCl solid makes up 0%, what do we say a number divided by 0 comes out to? Yeah, undefined. Why? Because it's insanely large. Now, nearly insoluble salts ionize very little when dissolved in water. Now, how can you tell if a salt is nearly insoluble? When you go to reference table F, this gives you the rules for which things are soluble and which things are insoluble. For example, anything with any of these ions will always be soluble with no exceptions. These guys are going to be soluble, but they'll have these exceptions. Now you might want to say, okay, AgCl is insoluble. That's not entirely true. Let's say you took a truckload of silver chloride and backed it up to Lake Ontario and dumped it in the lake. Of that truckload, maybe a thimbleful would dissolve in the whole lake. That's not technically insoluble, although it's such a pathetically small amount, it might as well be. It's called nearly insoluble. Now, under those conditions, we can compare their solubilities using what's called the solubility product constant, also known as Ksp. So here in this example, if when dissolved you have essentially none of these and a whole lot of that, KEQ will basically be 0. So how can you compare their solubility? Easy. Get rid of that number there. Taking a tiny number, dividing it by a huge number, isn't going to do us any favors. Let's take out the middleman. We're just going to multiply the products. Solubility product constant. That's right. Products. We only use the products, the dissolved ions. So, how do we set this up? To set up the Ksp, you have to know what ions that the salt is going to break up into, and write what's called the dissociation equation, where you take the salt and you break it up into its ions. Now, it's going to look like a decomposition reaction, but it's not a decomposition reaction, because you see, in decomposition, the compound breaks up into two elements. That's not what's going to happen here. What's going to happen here is the ions are simply going to be pulled apart from each other. They won't gain electrons, they won't lose electrons, there won't actually be any chemical reaction taking place. It's just a physical change. So when you take silver chloride and dissolve it, you get silver ions, and chloride ions. And that's what it breaks up into. So to set up the Ksp, we take the concentration of silver ions and multiply it by the concentration of chloride ions. You'd be given the solubility, you multiply it, and you'd get the Ksp. Calculating the Ksp will be beyond the scope of the course. What you need to be able to do is set up the Ksp expression and then compare Ksp values and figure out what it means. Let's do another. Lithium carbonate, when it dissolves, forms lithium ions, but not just lithiums, two lithiums, right? Two lithium ions. Plus, now remember, carbonate is one piece. It's carbon covalently bonded to 3 oxygens. Now, water can break the ionic bond between lithium and carbonate, but water cannot break the covalent bond between the carbon and the oxygen. So the carbonate will remain in one piece when it's dissolved in the water, and they will both be aqueous. So when we set up the Ksp expression, we'll have Li plus 1, and since there is a coefficient of 2, that becomes an exponent of 2, times CO3 minus 2. No coefficient, no exponent. And that's how you would set up the Ksp equation for lithium carbonate. Let's do one more. Lead 2 iodide, when dissociated in water, will form a lead plus 2 ion and 2 I minus 1 ions. Now you might be tempted to make it I2 because when iodine is by itself, it's supposed to be diatomic, Brinkelhoff, right? But remember, this is not a decomposition reaction. All we're doing is we're separating the ions. We're not removing iodine's electrons and turning it in to pure iodine, I2. All we're doing is we're separating the ions from each other. These are both dissolved in water, aqueous, and the Ksp will equal Pb plus 2 times I minus 1 squared. And that's how you would set up the Ksp expression, the mass action expression for the solubility product constant. Just use the products, the concentration of the dissolved ions. Just the same as when Keq, the higher the Keq, the further the reaction went, same thing happens with Ksp. The higher the Ksp, the bigger the numbers we're multiplying together, so the more soluble the salt is going to be. Which of these numbers would be most soluble? Well, which is the biggest value? It would be this one. That would be most soluble, because that means you're multiplying the biggest numbers together. The higher the solubility, the bigger the numbers you're multiplying, and so the bigger your answer is going to be. That's the most soluble. Most soluble. So which one would be the least soluble? 10 to the negative ninth. Now, as far as this class is concerned, you don't have to go any further than this. If you're in college and you're trying to actually do Ksp problems, I may have time to actually do a video on Ksp at another time.